శ్రీనివాస స్వామి వారి కళ్యాణ మహోత్సవం చక్కటి ఎండలో ఆహ్లాదకరమైనటువంటి మంచి సమయంలో స్వామి వారి కళ్యాణం ప్రారంభం కావాలని రైతులైనటువంటి భక్తులందరూ కూడా కళ్యాణ మండపం లోపలికి తరలివచ్చి ఈ యొక్క కళ్యాణ మహోత్సవాన్ని జరిపించాలి. తిరుమల నుంచి ఆ శ్రీవారు 7 కొండలకి గ్రామం తాలూకు ఊరు తరలివచ్చి మన గ్రామానికి చేసి మీ అందరికీ కూడా స్వామి యొక్క అనుగ్రహం పరిపూర్ణంగా కలగాలి అనేటువంటి భావంతోని తిరుమల దేవస్థానం వారు ఈ శ్రీనివాస కళ్యాణ మహోత్సవాన్ని ఏర్పాటు చేయడం జరిగింది. భక్తులందరూ కూడా ఈ కళ్యాణ మహోత్సవాన్ని ఆనందాన్ని స్వామి యొక్క అనుగ్రహాన్ని ముందుగా పాత్రభాగం కావాలని ఆ స్వామి ప్రార్థిస్తూ ఇప్పుడు శ్రీ శ్రీనివాస స్వామి వారి కళ్యాణ మహోత్సవం ప్రారంభం కావాలని అందరూ కూడా నిశ్శబ్దంగా ఈ కళ్యాణాన్ని నిర్వహించాలి. ఎక్కడైతే గోవిందనామాన్ని ఉచ్చరిస్తామో ప్రతి చోట కూడా అందరూ గోవిందనామాన్ని పడాలి. ఎవరైతే ఒకసారి గోవిందనాన్ని కీర్తిస్తారో వారి జన్మ ధరించి కర్మ నశించి జీవితం ఆలోచించి జీవనం పరిగణిస్తుంది. భక్తులందరూ కూడా తమ తమ చేతులు తెలుసుకునేసి స్వామి వారి గోవిందనాన్ని చెప్పండి. ఈ కర్మ ధరించి కర్మ నశించి జీవితం ఆలోచించి జీవనం పరిగణిస్తుంది. గోవింద
What happened? Why does every interview still ask about solid principles? I mean, it's 2025. Aren't you gonna pass it? Pass it, dude. Solid is everywhere. You know why microservices don't collapse under their own weight? Solid. Why legacy systems survive cloud migrations? Solid. Why do Google and Amazon use code bases? Solid. Here, join Scalar's masterclass on solid principles and make your code production and interview ready. So let's get this done now.
So you just mentioned that you want to learn Python. So do not learn Python in manual way in 2025, because learning Python in manual way will take you like 6 months of your time. On top of that, you will be ultra non-productive in Python, because when you use AI inside your Python, when you use AI tools to do your Python coding, you will be saving upwards of 95% of your time while you are coding, while you are debugging, while you are building web apps, and while you are scraping as well, right? So for tackling this same problem, we found like 10 useful tools for day-to-day Python development and Python work. So we have developed a program which is like absolutely beginner friendly. Even if you have zero knowledge in Python, you can join this program, and in 30 days you will be becoming pro of Python, that also using AI. You will be not becoming a Python developer, you will be becoming a 10x Python developer. And the best part, like we have democratized this program, so this 30-day program is just for rupees 199. Can you believe that?
The initials GPT stand for Generative Pre-trained Transformer. So that first word is straightforward enough. These are bots that generate new text. Pre-trained refers to how the model went through a process of learning from a massive amount of data, and the prefix insinuates that there's more room to fine-tune it on specific tasks with additional training. But the last word, that's the real key piece. A transformer is a specific kind of neural network, a machine learning model, and it's the core invention underlying the current boom in AI. What I want to do with this video and the following chapters is go through a visually driven explanation for what actually happens inside a transformer. We're going to follow the data that flows through it and go step by step. There are many different kinds of models that you can build using transformers. Some models take in audio and produce a transcript.
This sentence comes from a model going the other way around, producing synthetic speech just from text.
All those tools that took the world by storm in 2022, like DALL-E and Midjourney, that take in a text description and produce an image, are based on transformers. And even if I can't quite get it to understand what a pie creature is supposed to be, I'm still blown away that this kind of thing is even remotely possible. And the original transformer, introduced in 2017 by Google, was invented for the specific use case of translating text from one language into another. But the variant that you and I will focus on, which is the type that underlies tools like ChatGPT, will be a model that's trained to take in a piece of text, maybe even with some surrounding images or sound accompanying it, and produce a prediction for what comes next in the passage. That prediction takes the form of a probability distribution over many different chunks of text that might follow. At first glance, you might think that predicting the next word feels like a very different goal from generating new text. But once you have a prediction model like this, a simple thing you could try to make it generate a longer piece of text is to give it an initial snippet to work with, have it take a random sample from the distribution it just generated, append that sample to the text, and then run the whole process again to make a new prediction based on all the new text, including what it just added. I don't know about you, but it really doesn't feel like this should actually work. In this animation, for example, I'm running GPT-2 on my laptop and having it repeatedly predict and sample the next chunk of text to generate a story based on the seed text. And the story just doesn't actually really make that much sense. But if I swap it out for API calls to GPT-3 instead, which is the same basic model, just much bigger, suddenly, almost magically, we do get a sensible story, one that even seems to infer that a pie creature would live in a land of math and computation. This process here of repeated prediction and sampling is essentially what's happening when you interact with ChatGPT or any of these other large language models, and you see them producing one word at a time. In fact, one feature that I would very much enjoy is the ability to see the underlying distribution for each new word that it chooses. Let's kick things off with a very high-level preview of how data flows through a transformer. We will spend much more time motivating and interpreting and expanding on the details of each step, but in broad strokes, when one of these chatbots generates a given word, here's what's going on under the hood. First, the input is broken up into a bunch of little pieces. These pieces are called tokens, and in the case of text, these tend to be words or little pieces of words or other common character combinations. If images or sound are involved, then tokens could be little patches of that image or little chunks of that sound. Each one of these tokens is then associated with a vector, meaning some list of numbers, which is meant to somehow encode the meaning of that piece. If you think of these vectors as giving coordinates in some very high-dimensional space, words with similar meanings tend to land on vectors that are close to each other in that space. This sequence of vectors then passes through an operation that's known as an attention block, and this allows the vectors to talk to each other and pass information back and forth to update their values. For example, the meaning of the word model in the phrase a machine learning model is different from its meaning in the phrase a fashion model. The attention block is what's responsible for figuring out which words in the context are relevant to updating the meanings of which other words, and how exactly those meanings should be updated. And again, whenever I use the word meaning, this is somehow entirely encoded in the entries of those vectors. After that, these vectors pass through a different kind of operation, and depending on the source that you're reading, this will be referred to as a multi-layer perceptron, or maybe a feed-forward layer. And here, the vectors don't talk to each other. They all go through the same operation in parallel. And while this block is a little bit harder to interpret, later on we'll talk about how the step is a little bit like asking a long list of questions about each vector, and then updating them based on the answers to those questions. All of the operations in both of these blocks look like a giant pile of matrix multiplications, and our primary job is going to be to understand how to read the underlying matrices. I'm glossing over some details about some normalization steps that happen in between, but this is, after all, a high-level preview. After that, the process essentially repeats. You go back and forth between attention blocks and multi-layer perceptron blocks, until at the very end, the hope is that all of the essential meaning of the passage has somehow been baked into the very last vector in the sequence. We then perform a certain operation on that last vector that produces a probability distribution over all possible tokens, all possible little chunks of text, that might come next. And like I said, once you have a tool that predicts what comes next given a snippet of text, you can feed it a little bit of seed text and have it repeatedly play this game of predicting what comes next, sampling from the distribution, appending it, and then repeating over and over. Some of you in the know may remember how, long before ChatGPT came into the scene, this is what early demos of GPT-3 looked like. You would have it autocomplete stories and essays based on an initial snippet. To make a tool like this into a chatbot, the easiest starting point is to have a little bit of text that establishes the setting of a user interacting with a helpful AI assistant, what you would call the system prompt, and then you would use the user's initial question or prompt as the first bit of dialogue, and then you have it start predicting what such a helpful AI assistant would say in response. There is more to say about an added step of training that's required to make this work well, but at a high level, this is the general idea.
మీ నోటి దుర్వాసనని మీ గుర్తింపుగా మారనివ్వకండి. తీసుకురండి పెద్ద క్లోజప్. ఇప్పుడు కేవలం 55 రూపాయలకే. నెలంతటి తాజాదనం ఇప్పుడు కేవలం 55 రూపాయలకే. మీ నోటి దుర్వాసనని మీ గుర్తింపుగా మారనివ్వకండి. తీసుకురండి పెద్ద క్లోజప్. ఇప్పుడు కేవలం 55 రూపాయలకే. నెలంతటి తాజాదనం ఇప్పుడు కేవలం 55 రూపాయలకే.
Every idea you love began as nothing. Just a flicker on a screen, asking a simple question. What do you see?
In this chapter, you and I are going to expand on the details of what happens at the very beginning of the network, at the very end of the network, and I also want to spend a lot of time reviewing some important bits of background knowledge, things that would have been second nature to any machine learning engineer by the time transformers came around. If you're comfortable with that background knowledge and a little impatient, you could probably feel free to skip to the next chapter, which is going to focus on the attention blocks, generally considered the heart of the transformer. After that, I want to talk more about these multi-layer perceptron blocks, how training works, and a number of other details that will have been skipped up to that point. For broader context, these videos are additions to a mini-series about deep learning, and it's okay if you haven't watched the previous ones, I think you can do it out of order. But before diving into transformers specifically, I do think it's worth making sure that we're on the same page about the basic premise and structure of deep learning. At the risk of stating the obvious, this is one approach to machine learning, which describes any model where you're using data to somehow determine how a model behaves. What I mean by that is, let's say you want a function that takes in an image and it produces a label describing it, or our example of predicting the next word given a passage of text, or any other task that seems to require some element of intuition and pattern recognition. We almost take this for granted these days, but the idea with machine learning is that rather than trying to explicitly define a procedure for how to do that task in code, which is what people would have done in the earliest days of AI, instead, you set up a very flexible structure with tunable parameters, like a bunch of knobs and dials, and then, somehow, you use many examples of what the output should look like for a given input to tweak and tune the values of those parameters to mimic this behavior. For example, maybe the simplest form of machine learning is linear regression, where your inputs and your outputs are each single numbers, something like the square footage of a house and its price. And what you want is to find a line of best fit through this data, to predict future house prices. That line is described by two continuous parameters, say the slope and the y-intercept, and the goal of linear regression is to determine those parameters to closely match the data. Needless to say, deep learning models get much more complicated. GPT-3, for example, has not 2, but 175 billion parameters. But here's the thing, it's not a given that you can create some giant model with a huge number of parameters without it either grossly overfitting the training data or being completely intractable to train. Deep learning describes a class of models that in the last couple decades have proven to scale remarkably well, What unifies them is that they all use the same training algorithm. It's called backpropagation. We talked about it in previous chapters. And the context that I want you to have as we go in is that in order for this training algorithm to work well at scale, these models have to follow a certain specific format. And if you know this format going in, it helps to explain many